Hello, everyone. How are you doing? Welcome to Calculus. This is section R02, the 11 a.m. I'm Scott from the University of South Florida. I've been told that I need to say this every time I start streaming, and I forgot this morning at 9:30. Anyway, maybe I should put a post-it note right here. Don't forget to say your name and what institution you represent. And then they tell us that if you say that, then they have all these rules. By the way, I forgot to make Donald Trump jokes today. I'll hopefully remember next time because there's apparently someone going around putting on this. I don't want to say conservative because they're not actually conservatives. They're like right-wing nut jobs, which are different than conservatives. Conservatives are like modern people. I'm conservative, right? I don't like that, but I don't like it. These people are way over there, right? There's conservative, then there's, nutty, then there's really nutty, and then there's these people way over here. But they apparently have a list of professors, and it's my dearest ambition to get on this list of people that they call liberals or leftists or whatever they call them, mostly for the irony of the thing. So, anyway, I forgot to make Trump jokes today, and I'm sorry. I'll make them next time to get on the list. Anyway, that's enough yakking. Today we have, as our TA, we have Aruj. Say hi in chat, please. She is going to be answering your questions as they happen in chat. And I will also have to remember not to say anyone else's name because she's an employee. I get to reveal that she's in chat, but the rest of you I'm not supposed to because you're students. Are there any questions before we get started? Questions, comments, issues? Okay. 1 to 5, the quiz. Getting on the quiz and making the quiz happen. How did you feel about that? So I don't actually, I'm not asking about the quiz itself. I'm asking about the process of making Proctorio work. So just 1 to 5. How do we feel about the quiz? Paste. Like there we go. Um, no spaces. So again, not the quiz itself, just the process, right? So this is just making it so it's just the process, making Proctorio work. Okay, so we're getting used to that. We're still working at the bugs. You noticed a small little change. Also, we will be some kind of weird framing the camera, different issues. We'll talk about those. If you have issues about that, please come see me during office hours or during the problems that things do wrong. Also, remember, announcement at 5 p.m. The problem set session on Discord at 5 p.m. So don't forget that one. That's today. We have a test. It's supposed to be the final version. So we're going to put out answer sheets as soon as we can. If for some reason, I highly advise, it's not required, but I highly advise you print out the answer sheet for the test. The test is not this Saturday, but next Saturday at 9 a.m. You're going to be, it's going to be proctorioed, but you have to start it at 9. 8:55 is probably when we're going to start. And you have to end at the time we say. On the 11th, yeah. So not this Saturday, but next Saturday. And what's going to happen is that we're probably going to be on chat. I haven't worked all the bugs out of this, but we'll probably actually be on Discord with everybody's mics muted with a thing that says raise hand and stuff. So if you're having issues with Proctorio or something like that, we can deal with it then. We can deal with issues. We will have contingency plans. We will have live proctors available. If something happens, we'll have issues like, hey, I need to go grab some scratch paper. Is that okay? Those types of things. I won't be able to give you an extra pencil or an extra stapler but virtually I will, be there. And then there'll be other things like you're going to line up, and then, I'll give you evil professor look somehow if you try to turn in a quiz test with blanks and stuff like that. So we're going to try to make it as close to the possible. We'll have it so that the fat lady sings. And we're going to make it as close to possible as the regular test. Okay. So if you have any questions about that, please, by all means, ask them during office hours, and we will talk about it. Let's talk about the lovely quiz, okay? How do we feel about this first problem? 1 to 5. How do we feel about number 1? There was a lot of anxiety about this problem, and I want to talk about it. So 1 to 5 on number 1. How do we feel? 1s, 2s, 4s. Ooh, there's a nice flat, flat curve. A lot of people are streaming the 930 and not this one. That's curious. Okay, so this one's harder because most of the proofs we've done up to this point have had long strings of equal signs, and then I've asked you to make some words happen. This proof is harder. This proof has, the word to symbol relationship is, much more words and many fewer symbols. It's an argument, right? That's what a proof is, an argument about why something is true. So the way that I did it, and then there's another way to do it in the textbook, which is a proof by cases. The key to that proof is to make sure that you answered everything, that you checked all the cases. But this proof right here, this is the proof by contradiction. This is the one I like. I keep touching my face, don't I? And I'm not supposed to do that. But, what do you want? This is the proof by contradiction. And let's talk about it. So let me take me out of the picture for a moment, and let's talk about this proof. If f is, what do I want to show? I want to show that if f is continuous on the closed interval and differentiable on the open interval, and if the two endpoints are equal to each other, then there's some point in the middle, there's some x value in the middle so that f prime of u equals 0. So what I'm going to do, what my strategy for this proof is going to be, is simply going to be assume otherwise. Assume otherwise, right? And I really need to be in the scene for that, right? Because I have to do it right. Assume otherwise. So when I assume otherwise, I'm supposing that f is continuous on the closed, differentiable on the open, and the two endpoints are equal, right? Have the same y value. But I'm assuming that there's nothing in the middle. There's no x value, so that the y value, so that y prime is 0. Right? I'm assuming there's no x value in the middle so that the derivative at that x value is 0. All right. And then, again, my strategy is to hunt for the min and the max and finding a contradiction. And then I wrote down exactly what the two big theorems I'm going to use are. So, since f is continuous on AB, by the extreme value theorem, f must have a minimum y and a maximum y for that interval. How do we feel about that, 1 to 5? The use of the extreme value theorem to set up what I'm hunting for. Okay. All right, so I've got some differing opinions on that one. Okay. So I do that, and now I'm going to hunt for the min and the max. And I don't have to do this right here. I don't need to do, but I did. I did this a little formally. I said, let u be the x value so that f of u is the maximum. And x value, there could be multiple. But I just said it. I said it like this. So if u is in the middle, then by Fermat, since f is differentiable in the middle, f prime of u equals 0. So it can't be there. U's got to be at one of the endpoints, and that's that right there. Likewise, if the min occurs in the middle, then the derivative is 0 there. So the minimum must be at one of the endpoints. I can't have this situation, and I can't have this situation. But that means since f of a equals f of b, that means that the min and the max are equal. And that means that the function is constant, right? This is the min equals the max. If the min equals the max, everything's the exact same number. And that means the derivative is 0 everywhere. And that's absurd, okay? So there must be a u so that f prime of u equals 0. All right? How do we feel about that proof, 1 to 5? Now with the explanation. Do we have any questions about it, too? Any questions, comments, issues, thoughts? Okay. Okay. I've got some cries in the emote chat. Very nice there on Twitch. Any other questions? Okay. Will it be on the test? Maybe it's there. Maybe it's not. Maybe I gave you choice too. Maybe I asked you 4 different proofs, and this is one of them. Could have done that, you know. Could have asked you the mean value theorem proof. That's a good one. Could have asked you the proof we did last time at the very end. That's a really good one. I could have given you choice, right? We'll talk about the test and we'll definitely talk about it on Friday. So what are the big proofs? That's a good question because we haven't put out the study guide yet. The big proofs are the proof of Rawls' theorem, the proof of the mean value theorem, the proof of the what's the other one I did? The proof that if 2 functions have the same derivative, then they differ by a constant. And they can only differ by a constant. And then the proof that that if a function is strictly increasing, it can have only one root, or if it's strictly decreasing, it can have only one root. There are a couple of those things. They're all in that big section. So all the major proofs that can be on the test come from section 4.2 in your book. And 4.2 has a couple different ways to do some of them. So, for instance, the proof on page 211 in your book in section 4.2 is a proof by cases that's similar to this proof above, but slightly different. You may use that. Other proofs that can be on the test, the proof of the mean value theorem there on page 212, which I pretty much did verbatim odd chat last time. Made a few differences, but that's pretty much on the video from last time. Other proofs that can make it, that theorem 5 and corollary 7 together is a good one. And then what are the other corollaries? There's another one in here somewhere about the increasing, decreasing. And then the tests from 4.3 are all good ones. So the proof in section 4.3 of the increasing, decreasing test, and then the proof of so the first derivative test proof, and then the proof of the second derivative test is also a good one. I don't know if the second derivative test one is in here proofed. And we all have our favorites. So some instructors are doing some, other instructors are doing others. And I will try to put and yes, I will post the questions about, can I put the list on Canvas? Obviously I will. I'll put it on the study guide when we all agree to what the study guide's going to say. We were supposed to put it like we did for the, we're supposed to have agreed on the test. The test was supposed to be finalized yesterday, but, you know, we might argue about it a little more. Also, I'm trying to get you more time. There are a couple of us trying to say we should make it a 90-minute test plus time to do the uh, scanning, just to deal with any of the distractions. So I'll talk about that as the test gets closer and all that stuff gets finalized. Are there any other questions? Also, do I have any supplements for this unit, like I did for the other units? By which I think you mean notes or other videos and stuff like that. I will look. I may. Also, I will have. I think did. I post the other instructor videos. So if I posted the other instructor videos, I will. For some of the, and I will post these notes. So I will post the notes and the keys for the various classes. I don't have all the fancy LaTeX notes for stuff in Module 3, which is a shame because this would have been a good place to use them, but I didn't have time to make them this semester because they gave me a new class. And then they're giving me, I just got my assignment for next semester. I'm teaching, get this, 2 sections of pre-calc. 250-person sections of pre-calc. Yeah, so, and 1 section of calc so far. So, pity me. 2 math lectures. That's going to be fun. So I'm not going to have time to do stuff this week. You don't care about that because you're not in that class. Okay, moving on with life. Do I believe Marvin the Martian? The answer is no, I don't. I will talk about Calc 2 professors at length, but not over Twitch. You want to talk about that? That's an office hours questions. I'll give you good gossip. Anyway, so let's talk about why Marvin's wrong. Again, this is similar to one of the problems in the textbook, one of the examples in the textbook, and a bunch of the problems in the textbook. In fact, I think it is one of the problems in the textbook. Marvin says that 2x plus cosine of x can have no more than 1 real root. Do you agree or disagree? I said Marvin is wrong. Assume otherwise. Let a and b be 2 different roots, which means f of a equals 0 and f of b equals 0. F is continuous everywhere and differentiable area everywhere because it's the sum of 2 differentiable functions, right? One of them is a polynomial, the other one's cosine. Both of those are differentiable. That means it's differentiable and continuous. So by Rolle's theorem, there has to exist some u so that f prime of u equals 0. Well, what is f prime of x? F prime of x is 2 minus the sine of x. And the biggest sine can ever be is 1. So f prime of x has to be greater than or equal to 1. Okay? F prime of x is never 0. Right? So f prime of u must be greater than or equal to 1, contradicting the assertion that f prime of u equals 0. Therefore, Marvin's wrong. That's absurd. Marvin's wrong, and this function can have at most 1 real root. How do we feel about that, 1 to 5? How do we feel about that problem? Okay. All right. Name 1 memorable thing you found memorable from the last class. Tech worked this time. Knock on wood that it works this time. Any other questions, comments, issues, suggestions, thoughts about the quiz? Okay. Let's scroll up. Yes. Any other questions? Okay. I will post the key and I will post the notes. There you go. So you don't need to copy everything down right now. I forgot to post the key and notes last time, but I will do that this time. I even made a little note for myself. What did I do with my note? No, I lost my note. I did make a note for myself. Is this my note? No. Well, I'll make a new note for myself. No, I don't have a pen. TA will remind me to post notes. How's that? I'll make you. I'll get you to post a note. TA will remind me to post notes. All right. So anyway, any other questions? TA will remind me to post notes and key. All right. So all right. So let's move on to the new material. They're really synonyms. Let's see. Class. Okay. So last time we went over a bunch of proofs, and we did oh my goodness, 2 proof lectures in a row with no problems, just proofs and proofs and proofs and proofs lectures. Okay. So we're done with the proofs and proofs and proofs and proofs lectures, right? There's only one more big proof lecture, and that one's really cool. For the whole course, there's only one more of the really big proofy ones. Let's talk about something a little bit more practical. Let's talk about optimization, otherwise known as how to math your way through microecon. It's very good. You can get 2 semesters of micro out of one class, one lecture in math. So today's big idea, and there are all these different optimization problems in the book, okay? And I don't want to they've got cool ones for, physics. They prove Snell's law, give you a problem with Snell's law, and they do a bunch of other stuff. But really, what we have here is stick to one example, okay? So the example we're going to stick in mind, the model that we're going to use is that things cost money, right? I can't always get what I want, and I can't always get everything I want, right? But what we want to figure out is what's the way I could get the most of what I want, okay? Given the fact that things cost money, okay? Now, the key to these problems is, first, draw them. You need to draw them. The second thing is to ask yourself what costs money. And that's true even if the thing does not have money exclusively. So, like, one of the problems on peer leading, which I need to remember to post the peer leading packets as well, is one of the problems in peer leading is this idea that what I want to do is I want to minimize the surface area of a water bottle, okay? Now, if I'm minimizing the surface area of a water bottle, okay, why do I do that? Well, because aluminum costs money, or plastic costs money, right? So we want to figure out the optimal dimensions of things, okay? So this is the typical kind of setup, okay? The Renaissance Fair wishes to set up a rectangular area for employee parking. 3 of the sides will be visible to patrons, so the fair has to use a nice fence. However, the north side can't be seen by the guest area, so the fair will need a chain link fence. If the fair has a $1,200 budget, what is the largest parking lot that it can build, and what are the dimensions of that lot? Okay, so this is a typical kind of thing. I want parking area, but fence costs money. Okay, so given that I only have so much money, what's the biggest thing I can build? Okay, how do we feel about the setup of this problem, 1 to 5? 1 to 5, just the setup. Okay, so we feel pretty comfortable about setting up this problem and what it's going to look like. So let's talk about this. All right. Nope. I need the other one. How do I set, what's the first thing? I'm going to draw a picture. So let's draw a picture. Pull up the drawing menu. Let's draw a little picture. And there's a dual kind of setup to this problem. The other thing is that if I need 300 square feet of parking, what's the cheapest way to do it? We'll get to that problem second, but there's another way to think of this problem, right? But they're really the same problem. The making things biggest or finding the cheapest way to do something are really the same problem. So let's draw the picture here. And the picture is something like this. Okay? I have a nice little rectangle. That's my parking area. Now, I know that on 3 of the sides, I'm going to be using things that cost $20 a foot. Oops, nope, I want you to stay that color. So on 3 of the sides are going to cost me 3 of the sides are going to cost me $20 a foot. So I'm going to say this side costs me $20 a foot. This side here costs me $20 a foot. This side here is going to cost me $20 a foot. And this side here is going to cost me 10. Oops, I didn't want to look. Okay? And now the question is, what am I doing here, right? What do I want? I want area. Okay? So what I want is area. Okay? So let's write some equations down. Okay? Area equals what? What's the formula for the area? Yep, there it is. So A equals L times W, length times width. Okay? So I'm going to put that on my I'm going to put the length and the width on this thing. So let's see. I'm going to call this an L. I'm going to call this side here a W. Right? Length times width. That makes this green side over here one of the lengths. And that makes this blue side down here a width. Okay? How do we feel about that? The kind of setup, the idea that I'm looking for area, and that's length times width. So that this is L and that's W. How do we feel about that 1 to 5? The idea here that I've got length and I've got width. And that what I need to maximize is L times W. All right. And now things cost money. What costs money? Well, the fence, right? Well, what is the fence going to cost? This side here of the fence is going to cost what? What does the orange side cost? It's $20 a foot. And how long is that fence? That side? L. Plus, well, let's see. This side here, the side that's on top, is going to cost me 10W. Plus, well, the side that's in green over here is going to cost me 20L. Plus, this side over here in blue. Okay. So my entire cost equation is going to be 40L plus 30W. W. And this thing right here is fixed. Right? I have a budget. What's my budget? My budget is the 1200. Okay? So that means whatever my cost is, I'm going to wind up with 1200. So that becomes what's called my constraint equation. Right? The point is that 1200 at the end of the day is going to equal 40L plus 30W. Okay? How do we feel about that 1 to 5? Just the setup. That's part of the setup here. Okay. Now, my question is, what's going to be my area? I've got two variables here, and I've got two equations, right? And then I've got this kind of thing that I'm trying to optimize. The thing I'm trying to optimize is this area. Okay? So what I need is I need one dependent variable and one independent variable. But notice what happens. Whatever my width is determines my length. Okay? If my width is 10, right? That means I sub in that 10, I get 300, I subtract the 1200 from that, and I wind up with a number for W. Okay? If width is fixed, if width is fixed, I wind up with a number for L. Is everyone on board with that? The fact that this number here, whatever I pick, will determine that number there. So what I'm going to do is I'm just going to solve for that equation. And when I do that, I'm going to wind up with one equation and one unknown. Okay? Let's do that. Let's solve this sucker for one equation with one unknown. So now I'm going to wind up with 1200 and that gives me here that 1200 minus 30W equals 40L. Okay. And that implies that 1200 over 40 minus 30 over 40 W equals L. So here I just divided both sides by 40, and now let's clean it up a little bit. 1200 over 40 is what? Bueller. Bueller. There we go. Thank you. And the other one just became 3/4. So now I'm going to take that and I'm going to sub that into my thing. So now what I'm going to do is I'm going to sub in So now what I'm going to do is I'm going to sub in for L. Okay? Sub in for L. So what I've got is I've got that A equals length times width, which equals 30 minus 3 over 4 W times W. And now I'm going to simplify it because I'm going to take a derivative. And that's going to equal 30 W minus 3 over 4 W squared. Okay. How do we feel about that 1 to 5? Now I have one equation, right, for A. Okay. All right. So now that I have one equation for A, I'm going to take the derivative and set it equal to 0. And why am I doing that? Well, what I'm trying to do is I'm trying to find an optimum, right? Here's this equation. Let's clean this up a little bit like I did. I have this equation, 30w minus 3 over 4 w squared. Okay? So I have this equation that my area is this right here. And I want to solve for the maximum. Now, what happens at the maximum? What's the motto for this test? What's the motto for the test? When in doubt, do what? Motto for the test. I want someone to write it in chat. Motto for the test. Yes. If all else fails, take the derivative and... Yes, there it is. Derivative equals 0. So, all else fails. If I don't know what I'm doing, I'm going to take the derivative. I'm going to set it equal to 0. Right? Because look at what's happened here. This is the area for any given width. So if my width is 10, right, that's going to determine an L, and that's going to give me 225 square feet. Likewise, if my width is 30, that's going to give me a different L, and I'm going to wind up with 225 square feet. But if my width is 20, I'm going to wind up with 300 square feet, and that's the absolute biggest I can do given this budget. Okay? So I'm maximizing the area. What I do is I take the derivative and I set it equal to 0. So let's do that. Times w to the 0 minus 2 times 3/4 w to the first, which is the same thing as 30 minus 3/2. Duh. Brain is dying. And then because I've taken the derivative and setting it equal to 0. So I'm going to optimize it by taking the derivative and setting it equal to 0. How do we feel about that, 1 to 5? This idea that what I'm doing is optimizing. And what I'm doing to do that is take the derivative and set it equal to 0. How do I feel about that, 1 to 5? Okay. Uh-oh. What happened? Oops. There we go. All right. So now what I'm going to do, I've got the derivative. I set it equal to 0. Let's solve. Let's solve for w. So that implies here, oops, wrong color. Pick up the right pencil. That implies, I really wish, if someone could get on this, I'd really appreciate it. I really wish that I could have multiple markers, each one like $30 a pop, where they're pre-programmed at different colors. So I could put them down here. I could put a little piece of tape here. I could put it there on my screen and then, pick up the right color, just like I would in real life. It'd be nice. I'd probably only have 2 or 3 of them because they were $30 a pop. But it'd be nice. So, one of you guys get on this. It'd be a nice thing to have. Anyway. So what I've got here is I've got the 30 minus, this is going to mean that 30 equals 3 over 2w. Okay, and then so multiply both sides by 2, divide by 3, and I get that, so this is 60 over 3 equals W, and that implies that 20 equals W. Now, I'm going to put a little star here. And the star means that I've optimized. That's my optimum. Now, I want the length back, too. So I'm going to plug that into the equation as well. I'm going back to my original constraint equation, and I'm going to get that 1200 equals 40L plus 30W. So that means that 1200 okay. And that, of course, means that this right here, so this means that 1200 equals 40L star plus, that's not a prime, that's a star, plus 30 times 20, which means that this is still 40L star plus 600, which means that subtract both sides. That means 600 equals 40L star, which implies that L star equals 15. Okay, how do we feel about that 1 to 5? I got the other dimension. Okay, solving for the other dimension, 1 to 5. And of course, what I want to do then is I want to take this and I want to plug both of these back in. So I take you and I take you, I move them all back here, and I get the fact that the area A star, not A prime, A star equals 20 times 15 equals 300. Okay, so there's one answer. Oops. So there's one answer there. There is one answer there. And there's one answer there. Okay. Now, there's one more detail. Okay. I have my answers. There's one little detail I need to work on. That is, do I know I have a max? Okay. There are 3 ways to check it. I'll write them out. The 3 ways to check it are the following. So I need to check to make sure I have a max. Okay. Method 1, check endpoints. Okay. Here, I'm maximizing. Right? I can't have negative width and I can't have negative length. So I check my endpoints. L and W both have minimums of 0. And if L equals 0, then A equals 0. And if W equals 0, A equals 0. So those are not, and both of those are less than 300. Okay? How do we feel about that? 1 to 5. And I only have one critical value. All right, I just have to make an argument. This is why I found the max. Okay? I don't know why this became like it did, but it did. Let's see. Can I move over, please? Okay. I went and I spent money on this mouse. Okay. I actually went and spent money on this Arc mouse, which is supposed to let me like shift over and up in this program because I don't have a touchscreen monitor on the broadcast screen, and it seems to be a waste of money. This may be going back to Amazon because it doesn't really work when I have the glove on. That's annoying. What I should get is a touchscreen monitor over here. But those are more money. Okay. So we feel pretty good about that. Next method. Second derivative test. Okay. So what I do is I do a double prime equals, where is it? Sorry. There's a prime. So a double prime, or dA over dW, d squared A over dW squared equals, there's a little, okay. I take the second derivative and I wind up with 30. That goes away, and I wind up with 0 minus 3/2, which is less than 0. So this function is concave up. I'm sorry, concave down. And I have a max. Okay. Third way to do it would be the first derivative test. That's kind of a pain. Right. So the first derivative test is that I take the, I take my maximum point, which was at 20, and I test the stuff around it. So I take a test at, I take my test at, say 10 and 30, right? Let's do 0. Yeah. So 10 and 30. So A prime for this test was 30. A prime of 10, forgive the notation abuse, equals 30. 30 minus 3/2 W. So that's 10, which equals 30 minus 15 equals 15, which is greater than 0. So I've got a positive here. which means that A is increasing there, and A prime of 30 equals 30 minus, this is going to be 45. I should write it 3 halves, 30, which equals 30 minus 45, which equals negative 15, which is less than 0. So I've got a negative and I've got decreasing, so I have a max. Okay. And so I just want to pick my method. So are there any questions about that? 1 to 5, how do we feel about those 3 tests that I could do those? So 1 to 5, how do we feel about the endpoint test? And then 1 to 5, how do I feel about the second derivative test? And then 1 to 5, how do I feel about the first derivative test? So three polls are about to go up. The first one is method 1. The second one is method 2. And the third one is method 3. Okay. By the way, there's a question in chat. Do I have to do all of 3 tests or just choose one? No, I don't have to do all 3 tests. I picked the one I like the best. So now some of these tests may not be available for certain problems. Okay. So for instance, if I had endpoints that were infinity, I would be in trouble. Yes, I could scroll up. I can also make the whole thing bigger. What I can't seem to do, there we go. And then last but not least, so I can do any test I want as long as I show that what I found is a max. Now, sometimes the endpoint test is not available because I don't have hard endpoints. I've got soft endpoints. That's especially true when we minimize things. When we minimize things, we usually wind up with endpoints that are infinity on either side. So you have to choose, you wind up with soft endpoints, and because you've got things in denominators, and you have to use one of the other tests. But the endpoint test is nice, especially when you only have one. If you only have one critical value, especially when you're maximizing things, you tend to only get one critical value that makes sense. And if that's the case, these endpoint tests are really nice. Because they're quick and easy, right? And like this one wound up being 0 and 0 at both endpoints. So, boom. Sometimes, however, you have to do the second derivative test is really nice when things have second derivatives. But if I wound up with a critical value where the derivative was not defined, and this happens a lot in economic problems when you're talking about wages, and hours worked. You wind up with corners when you do these problems. And the optimal solution is for people to work 40 hours a week because they get a big jump in benefits at that point. So you wind up with these situations where a place where the derivative doesn't exist, and you can't use the second derivative test there. You have to use first derivative tests, or you have to wind up using the first derivative tests on the stuff around it. But the second derivative test really fast, and endpoint checks really fast if you can use them. First derivative test you can pretty much always use, except it's ugly. It takes longer. All right. Any other questions about that? Did I scroll up there? I don't want to say your name. Did I scroll up there enough? And I will post the notes. My TA is going to remind me to post the notes. Okay. So let's look at this function let's look at this problem again. So how do we feel about this whole problem, 1 to 5? Wow. I've got some serious lag going on, don't I? How do we feel about this whole problem, 1 to 5? All right. Let's look at it from a slightly different perspective. Let's look at the exact same problem, but let's go the other direction. Okay? So the other direction would be to minimize the cost. Let's see. This problem I'm not going to get to. It's a really cool problem. I can't spell maintenance apparently. We'll get to that one. This will probably be homework because I didn't get to it. And I may do a video example of it later. But this problem right here. This is the exact same problem, except now what I'm going to do is I'm going to say I need 300 square feet, and I'm going to find out how much it's going to cost me. Okay? So 1 to 5, how do we feel about the new problem? What I'm trying to do. Okay. So, the new problem, the new setup, 1 to 5. Now, okay. All right, well, there's some questions going in chat. No, you're not quite working backwards. I'm going to answer these new questions. You're not quite working backwards. The question is, for the new problem, is it working backwards? No, it's working slightly differently. The problem is dual. And let me show you what I mean by that. The setup is pretty much just the same, right? For this bit right here. Is everyone on board that this bit right here is exactly the same? Okay, I'm going to have the parking areas are just the same setup here. This is so just the same that what I'm going to do is I'm going to click copy and I'm going to click paste. I got stuff that I didn't want here. But most of this setup here, the picture is still going to hold. This, however, I'm no longer optimizing here. So I need to erase some of this stuff. This is no longer fixed. This is no longer optimized. This all needs to go away. But the rest of the stuff I can keep. Okay? Now what I'm going to do is I've got a fixed area. And what I'm going to optimize is the cost. Okay? All right. Okay. So the setup's the same otherwise, right? It's still, if the fair needs 300 square feet, right? So now what's fixed is the 300, right? Not the amount of money I spent, right? One of the problems is your boss comes to you with a budget and says, get the most you can for this amount of money. This is what we're going to spend on parking. The other way this works is that your boss says, okay, we really need 300 square feet of parking. 300 square feet of parking. How much money is that going to cost me? Okay. Now, really what your boss wants to ask is what's the relationship between the amount of money and the amount of area I get. And we'll get to that next time. But for today, let's just look at this. Okay. So here I've got a fixed area. And that fixed area, which will be the constraint, is 300 equals L times W. Right? Before my constraint was cost. Now my constraint is different. Now my constraint is the area. Okay? So let's look at that. Now, so here's what we're going to do. We are going to work out that we're going to work out here, this right here implies the relationship between L and W is as follows. We're going to have L equals 300 over W. Now, if I've got L equals 300W, now I'm going to sub that in back into this equation here. And I've got that C equals 40L plus 30W. That came from above. So now when I combine these two, the other thing I want, when I click the back of the pencil, the other thing that would be great is if I click the back of the pen, if it would change colors. Either one of those would be awesome for me. Okay? So now what I'm going to do is I'm going to combine these two equations, and I wind up with the following. Okay. Now I'm going to simplify for taking the derivative, but one thing I want you to note here, okay? One thing I want to do is I want to make a note here. You see this 300? And you see that 30? When I take the derivative and set it equal to 0, things are going to happen, okay? Things are going to cancel, so don't multiply this out, okay? You need to convert the power to take the derivative, but don't multiply it out, okay? Leave it as 40 times 300 over W plus 30 times W, okay? Don't multiply those constants together, that 40 times that 300, because stuff is going to cancel later. Just hold on to it like it is, okay? So this thing, when I want to take the derivative, I'm going to wind up with 40 times 300 times W to the negative 1 plus 30 times W. Hold on to those constants. So now let's take the derivative and set it equal to 0. Well, all of these are just constant multiples. Okay? So when I do this, I'm going to wind up with 40 times 300 times negative 1 times W to the negative 2 plus 30 times W to the 0. I'm going to set that equal to 0. Okay. All right. So I set that equal to 0. And remember what I said about keeping those things in there? Okay, watch what's going to happen. This implies, since this is 0, I'm going to take this. Now you see this negative 1 here? There's a negative 1 right here. Okay, that means this whole term is being subtracted. So I'm going to add it to the other side, and I wind up with 30 equals 40 times 300 times W to the negative 2. All right? And that W to the negative 2 is really over W squared. Now, I'm going to divide both sides by 30. And I wind up with 1 equals 40 times 30 times 10 over W squared. Okay? Now I'm going to multiply W squared over by both sides, and I'm going to multiply that out. And that is going to get me that W squared equals 400. And that means there that W equals 20. Why not plus or minus 20? 1 to 5, how do we feel about that process? And of course, why not plus or minus 20 is the other question. Yes, I can't have negative fence. Exactly. So we've got the 1 to 5. How do we feel about that process? That's right. Okay. Now, the question is, what does this thing look like? Right? I want a minimum. I need to check that I have a minimum. Well, I can't do right. I can't do here. I'm going to have a situation where I wind up with infinities. Okay. So here, let's look at this equation. Okay. So here I had y equals 30w, and I had a max. Okay. Here I'm going to wind up with y equals, where y is cost, equals my original equation was 40 times 30 over w plus 30w. And I can't do that. I got to do a y here. There it is. Whoa. So my curve looks something like this. Okay. So this is what my curve looks like. And you can see here that my minimum value, I did this wrong, didn't I? What did I do wrong? That should be a 300. I'm sorry. That makes a big difference. Okay. So over here is my cost. Okay. So if I choose 10 as my width, okay. So if I chose 10 as my width, this parking area would cost me 1,500 bucks. Now, notice as my width gets smaller, this thing shoots off to infinity. In other words, it'll cost me an infinite amount of money as I get, right? If I get to 2.44, I wind up with I better wind up with a cost of around $5,000. Likewise, if I zoom this out, I'm going to wind up with really big costs as I make W bigger and bigger, bigger, right? Because my length is going to get smaller, and I'm just going to wind up with really big costs. Okay. Ignore the negative side of this. As I said, these things can have two sides, but of course the negative side doesn't make any sense. Now, Here, I can't use endpoints. Is everyone on board with that? 1 to 5. How do we feel about the fact that the endpoints wind up being infinite? Okay. So I can't use the endpoints to do this. I need to use a different method. So when I want to check that I have a min, okay. When I want to check that I have a min, I need to use one of the other tests, and the easiest one is the second derivative test. Right. So here I had a -1. I'm going to pull that out. I'm going to wind up with -2 times -1 times 40 times 300 times w to the -3 plus 0. I care about none of this. The only thing I care about, not none of this, the only thing I care about is the fact is these two terms right here. I got positive number, w has to be positive, right? And I've got two things here. Right, I got two things here that are going to wind up being a positive number. So I've got neg times positive times positive times positive equals positive. The only thing I care about is the fact that this is going to be greater than 0 when w is greater than 0. So my curve has come to them. Now, check to make sure you answered the problem. Okay, what did I forget to do? Oop, I forgot to sub back in. The optimal dimensions. Costing, what's my cost function here? Let's see, costing, and then C equals 40 times L, which is 15, plus 30 times 20. So that equals 12. Costing 1,200 bits of dinero and probably some American money too, as Chevy Chase would say. 1 to 5, how do we feel about this? I know people are asking questions, and that's fine. I will speak to them in a moment. 1 to 5, how do we feel about this? Okay. Yeah. So they're dual questions, right? And I wind up with the exact same dimensions, whether I'm minimizing, because, I made the numbers work out like that. I wind up with the same dimensions, whether or not I'm minimizing the cost, right? The relationship between W and L is the same, whether I'm minimizing or maximizing, right? That doesn't change. And that's what we're going to pick up next time, okay? At home, I'd like you to try this problem at home. I was going to try to get to it. I may make a video about it if I remember over the weekend. I'd like you to try this problem at home. And don't forget about peer leading on Friday. On Monday, we're going to do L'Hopital's rule, the big boy version. There's a problem on the problem set, which has been posted, that requires it. I trust that you can look it up. So we'll do the last little bit of L'Hopital's rule. We'll do a special trick with L'Hopital's rule. And that's and then there's a student calling him or herself dumb in chat. Please don't do that. You're not stupid. This is very hard. It's takes a while to get it. And I'll talk to you about it in office hours, which are next, if you wish. But please don't call yourself stupid. This stuff is really hard. So play with this here. Also, I posted WebAssign. I haven't posted all the WebAssign yet. Because I didn't get WebAssign posted until early this morning, I made it shorter. And then I'll post more problems for Sunday night. We'll talk about L'Hopital's rule, and then we'll do more optimization problems on Monday. Are there any other questions? Comments, issues, suggestions, or thoughts? Okay. In that case, what I'm going to do is I'm going to get out of chat. I went 2 minutes over, and I'm sorry. I probably started late. I did. So I went 4 minutes over total, and then I will answer any questions that you might have in voice chat. My office hours are now, so feel free to stick around. Also, I will post notes.